You see the headlines every day. AI seems to be advancing at this relentless, unstoppable pace. But what's really going on under the hood? What are the deep structures that are actually driving all this progress? Well, in this explainer, we are going to build a unified theory, one that connects the highest level, most abstract mathematics all the way down to the silicon that powers these models. So let's just dive right in. The central puzzle is this. We know for a fact that there are absolute mathematical limits to what any computer can ever do. And yet, AI seems to just blast through what we thought were barriers year after year. So, how is that possible? How can progress feel exponential when we know its foundations are provably finite? What's the trick? Well, the answer isn't some single magic bullet. It's actually a really elegant four-layer process. The best way to think about it is like a funnel. At the very top, you've got this absolute outer boundary, defined by pure computability theory. Then inside that, you have a more practical boundary of what's actually feasible to compute. Driving the progress within that feasible zone is an empirical engine, the scaling laws. And finally, the consequence of that engine is this constant pressure that literally reshapes the hardware, the architecture of our computers. So here's our game plan. We're going to start at the highest level of abstraction, computability, and then we'll narrow our focus to what's feasible. From there, we'll look at the real-world engine of scaling, and finally, we'll see how that all impacts hardware architecture. Let's get started. First up, that outer boundary. And really, we have to begin where Alan Turing himself did, by asking a very fundamental question. What does it even mean to mechanize something? And what are the absolute hard limits of any rule-based system, ever? And this is just a fascinating insight. It turns out, intelligence isn't some final destination we can just solve and then mechanize forever. It's a process of climbing up through layers of abstraction. Think about it. Once we mechanize arithmetic, the truly intelligent work becomes algebra. Once we mechanize algebra, it becomes calculus. Every single time we automate a task, the human work of guiding that automation just moves up to the next level. Now, to put this in more formal terms, we can think of our current capabilities as a single computational layer. Sometimes this is called an oracle stage. Just picture it as a black box that can magically answer any question that's solvable by our current set of rules. We'll call this layer N. But here is the absolute key. Every single one of these layers has a boundary, a set of problems that it fundamentally cannot solve. This limit is formally known as the Turing jump. It's like a wall that you simply can't climb using the tools you have inside your current layer. It represents what is uncomputable from where you stand. So how in the world do we make progress? Well, it's through a process that's been called step mechanization. We essentially find a problem that was previously on that uncomputable boundary, unsolvable in our layer N, and we figure out how to mechanize it. That single act creates a new, more powerful computational layer, N+1. But this new layer isn't the end of the road. It immediately has its own, even higher boundary, and the whole process just repeats. Progress is this endless, recursive climb. Okay, so that's the absolute limit. But let's be real. Most of the action in AI isn't about what's computable in infinite time. It's about what's feasible to compute within our lifetimes. So let's move to the inner boundary of our funnel. And you can see the key difference right here. Computability theory, that outer boundary, asks what's possible in principle, even if it takes a billion years. Its ultimate limit is the famous halting problem. But complexity theory, our inner boundary, asks a much more practical question. What's solvable efficiently? This is the world of P versus NP, the great unsolved question of whether finding a solution is fundamentally harder than just checking one. This table really visualizes the funnel for us. We start with this huge universe of all well-defined tasks. Then only a fraction of those are computable at all, even with unlimited time. But the zone where modern AI actually lives and breathes is an even smaller subset. It's the tasks that are solvable efficiently, in what computer scientists call polynomial time. So if step mechanization it was about climbing the ladder of what's theoretically possible, this concept, staged bounded ascent, is about climbing the ladder of what's practical. It basically means we're just getting smarter and smarter at finding shortcuts. Instead of trying to brute force these impossibly complex problems, AI progress is all about building frameworks that can find good enough solutions efficiently. It's about navigating these vast search spaces without getting hopelessly lost. Okay, so we've got our theoretical boundaries marked out, but what is the actual engine that's pushing progress forward inside that feasible zone? Well, this brings us to the empirical heart of the whole thing, scaling laws and the hidden superpower of efficiency. I'm sure many of you have seen a graph that looks something like this. It represents the famous power law of scaling. The idea is simple. As you increase the compute you throw at training, that's the horizontal axis, the model's error, or its loss, goes down predictably. This is what makes AI progress forecastable. But you'll notice the curve starts to flatten. That's the law of diminishing returns, right there in action. But, and this is so important, here is the secret to their unreasonable effectiveness. The C for compute in that law, it isn't physical work, it's logical compute, an abstract measure of the model's internal operations. The practical cost, the actual physical burden of time and power and money, is a completely separate thing. And that separation is the key because it means we can make progress just by getting more efficient at turning physical resources into that abstract logical compute. And this is why that separation matters so much. Just look at these curves. They all follow the exact same fundamental scaling law. But the rate of progress is wildly different. The difference between that top dashed line and the bottom solid line isn't a better model. It's a faster rate of efficiency doubling in the software and hardware stack underneath. Getting more logical compute for the same physical cost dramatically speeds up the journey. Efficiency is not a footnote, it is the fuel for this engine. So let's follow this pressure. This relentless demand for more and more efficient logical compute doesn't just happen in a vacuum. No, it exerts an immense, tangible pressure on the very design of our computer chips. Now, to really understand this, we need a new concept, the value scalable fraction, or just S. This is not the same as the part of a workload that you can run in parallel. This is the share of the work where adding more compute actually creates real value, like better model performance, new abilities, or higher accuracy. And in modern AI, this fraction, S, is huge, and it's growing all the time. So here's what that means for the people designing hardware. In the constant battle between flexible hardware, like a GPU, and fixed, specialized hardware, this little formula is the referee. It tells you exactly how much more efficient a specialized chip needs to be to justify its own inflexibility. And look what happens. As S, the value scalable part of the problem, gets closer to 100%, the required efficiency advantage, R, goes to infinity. Basically, when value can come from anywhere, flexibility almost always wins.
This race diagram is the big payoff. It shows that as the value scalable workload S grows, which is exactly what's been happening in AI for years, we get pushed deeper and deeper into this collapse region. And in this region, the best strategy isn't to build more and more fixed, specialized accelerators. The optimal move is to invest in flexible, programmable hardware, like GPUs, that can actually keep up with the constantly moving frontier of where value is being created.
Okay, let's pull all the way back out and assemble all these pieces. We've looked at 4 pretty distinct layers, right? From pure theory to concrete engineering. Now let's see how they fit together as a single, co-evolving system. And here it is, the full funnel of progress. Computability sets the entire stage. Feasibility then defines the practical arena where we actually play. Scaling laws give us the predictable engine that drives us forward inside that arena. And finally, architecture is constantly adapting to the pressure from that engine, making sure the whole system can keep on moving. They all work in concert. So, what are the big takeaways here? First, AI progress is not magic. It's a structured, layered process. Second, that progress happens fundamentally by climbing layers of abstraction. Third, this whole dynamic creates a relentless race in hardware between fixed specialization and flexible programmability. And maybe most importantly, these constant efficiency gains are the hidden engine that allows us to overcome the diminishing returns that are baked into the scaling laws themselves. So what we have is a powerful framework, a lens for understanding how our theories about AI and the machines we build to run it are evolving together. And that leaves us with one final, and I think pretty provocative question. If this is the structure of progress we've seen so far, what's the next layer that we haven't even conceived of yet?